Hey everyone, today we're going to go over mutual recursion and tree counting in part 2 of tutorial 4. We'll be going in depth on one of the hardest assignment problems to date, which is assignment 3, problem B, part E. So first, mutual recursion. The idea is that when we want a recursion to do two things, instead of having a function f that calls itself, we can use two functions f and g which call each other. So somewhere in the function body of f, g will be called, and somewhere in the function body of g, f will be called, and we'll keep doing that until we reach either a base case of f or g where the function can be evaluated. If you want to see a concrete example of this, Rivers gives an example in tutorial 4 along with some associated problems. So if you recall the definition of an undecorated binary tree, you'll remember that an undecorated binary tree is either empty or a node containing two trees, the left and right subtrees. What's interesting about this definition is that it's recursive. A tree is just defined in terms of trees. What about a mutually recursive data structure? So you don't even have to get out of the world of trees. We can think about general trees. This tree, for example, has a subtree, has three subtrees on this node from the 7 node, but only one subtree from the 5 node. Both of these things wouldn't be possible with our definition of the binary trees. One possible definition is that a forest is a multiset of general decorated trees, and a general decorated tree is a node containing a value in a forest. So in this example, 4 is, this whole thing is a general decorated tree. 4 is a node. This node contains 4 as a value. 4 is not the node. There's a node with 4 as a value. And then this is another tree, 5 and 6. And this is another tree, 7 with 8, 9, 10. So these two trees together are the forest of the topmost node. Similarly, this next node has 7 as a value and has 3 trees of size 1 as its forest, its associated forest. So the reason that this, I've just said hint here and not example, is because you can implement this in Racket on your own as an exercise, as an example. Here's the fabled problem from assignment 3, tree count of n. So our goal in this tutorial is to define a function tree count that returns the number of undecorated binary trees of size n without using the formula. The intention, if there was any in this problem, is that people would use recursion to count the number of possible trees. What some students did was go onto Google or work it out on their own or ask a friend and found a formula where they could easily use factorials and combinations to compute this number directly. That's fine, but you might be interested in knowing the recursive solution. So at the end of this video, you should be able to not only write your own tree count recursively, but also be able to apply that technique to more general problems. Let's start with a plan. How do we count the trees of size n? Well, when size is 0, that's very easy. There's just the empty tree. When size is 1, we have a single tree. When the size is 2, it's still fairly easy, but a little more complicated. You have the root node, and then one more node, and that node can go either on the left or the right. So 2 trees. N equals 3 is the first really interesting case. It has 5 trees. So I've drawn them out here on this slide, and I've drawn them in a very specific order. And this may be kind of the natural order that you're going through if you want to enumerate them algorithmically. You say, I'm going to go left as much as I can, and then I'm going to backtrack to where I can go right, and then I'm going to backtrack again and go right, and then I'm going to backtrack again, go right, and then go left, and then I'm going to go right and right. So this backtracking idea is pretty common in recursion, but we're going to do something a bit more amenable to an implementation in Racket. So if you'll notice this first tree, these two trees have something in common. This tree is kind of special, and these two trees have something in common. And that something in common is that this tree has a left subtree of size 2 and a right subtree of size 0. This tree has a left subtree of size 2 and a right subtree of size 0 as well. This is the only tree where it has two subtrees of size 1. And then these two trees share the property that they have right subtrees of size 2 and left subtrees of size 0. So what are our observations from this? Well, 1, every tree has a root. 2, the total size of the tree is the sum of the sizes of the two subtrees plus the size of the root, which is just 1. Our third observation is that the size of each subtree is at least 1 smaller than the size of the tree. In this example, it was exactly 1 smaller, or sorry, these subtrees, the subtrees of size 2 are exactly 1 smaller. This subtree, this empty subtree, is much smaller. And then these ones are 2 sizes smaller than the size of the tree. So 3 and a 1 and 1. It appears that we may have hope for a recursive solution because we can compute tree count n by using the values of tree count of smaller sizes. And what I mean by that is that to count the number of trees of size 5, I could have just said, I'm going to group these two guys together, these two trees together, as the trees with left subtree size 2 and right subtree size 0. And so I would do 2 times 1 to get all the possibilities for these two trees. And then for this second category, subtrees of size 1 and 1, I would do 1 times 1 to get all the possibilities. And then for these two trees, I would do all the subtrees of size 0 on the left and 2 on the right. So I would get 2 times 1, or sorry, 1 times 2. And I've put this information into a table for trees of size 3. So these are how many subtrees, how many nodes are on the left subtree and how many nodes are on the right subtree. And this is a enumeration. I've just written down what I've spoken on the past slide. So tree count 3 is 2 times 1 plus 1 times 1 plus 1 times 2, which is 5. How can we apply this thinking to n greater than 3? You might want to pause the video here and compute using this method, just writing tree count of some size times tree count of another size plus for size 4, and then for size 5 as an exercise. Here it is. So if we define, this is how we will apply this thinking to trees of any size. First, I'm going to define some notation to make it a little bit easier to talk about. We'll call Cn the tree count of n, so the number of trees of size n. So C0 is 1, C1 is 1, and if n is greater than 1, these two examples are just because there's only one tree of size 0 and one tree of size 1, the single node and the empty tree. And if n is greater than 1, then Cn is this formula. Cn is Cn minus 1 times C0 plus Cn minus 1 plus C times C1 plus into Z plus C0 times Cn minus 1. This pattern is almost reminiscent of some of the sum2 and other Taylor recursive examples we've seen, where you have two quantities and you switch them and do some computations on them. You increase one and you decrease the other. So how this works is by enumerating all the possibilities for the left and right subtrees. So here's the idea. If we had a function that could count the trees of size less than n, then we could use that function to go through all possible subtree sizes. But also, if we had tree count implemented using tree permute could be implemented using tree count. What I mean by that is that tree permute is what the name I've given to doing this operation. I'll say tree count of n is tree permute of n minus 1 and 0. And that's when I'm going to take n minus 1 and multiply it by 0 and go through all the possible combinations. So that's what I'll call tree permute. And then tree count n is just evaluating one of these c's. So tree count uses tree permute, and tree permute uses tree count. That sounds like it could be solved using mutual recursion. I'm going to show you an implementation right now in Racket, but it won't be in the notes or the slides. My challenge to you is to try it out after using the 30-minute rule. So what the 30-minute rule is that you wait 30 minutes after you've shared ideas with someone, or someone has shared their ideas with you, before writing it down. Because if you write it down directly after, you'll just have been writing what you memorized and not what you understood from that conversation. If you want to write something in your own understanding, you should introduce a time delay, and then you won't remember exactly what they said, but if you understood the ideas, you will remember those and write them down in your own words. So let's go into a blank Dr. Racket and write out this function. So you'll notice that I'm in full Racket. Tree create n. Going to define, that's our first function that we need to define. And I'll do it exactly as I've said in the previous slides. So we're going to check if n is less than 2, so that's when n is 1 or 0, we're going to return 1. Otherwise, we're going to call tree permute, which I'll define in a minute here, tree permute of sub1 n, 0, and 0. These values will make sense in a minute. And define tree permute, and this is the function that will add up all the possible values for the subtrees, which in turn gives all the possible values for the trees. So I want a left, I want a right, and I want an accumulator. And these are just the heights of left and right. Sorry, not the heights, the size of the left and right subtrees. Now, since we start out left, since we start at the left at n minus 1, and we're going to decrement it by 1 every time, when left is 0, that's when we can return. So we're going to return the values tree count left, multiplication between tree count left and tree count right. And tree count right will always be tree count of n minus 1, and left will be tree count of 0 at our stopping point. And we're going to add those to the accumulator so that the trees that we've already counted. And I'm going to indent this a little bit more to be a little more understandable. So if the left is 0, that's our stopping condition, we're going to return this sum. And then otherwise, what are we going to do? Well, otherwise, we're going to call tree permute. I've written an equals instead of a dash there again. We're going to decrement our left value. We're going to increment our right value. So this is moving in the picture of the trees. This is moving from one row down to the next row. So moving from 2 and 0 to 1 and 1, or moving from 1 and 1 to 0 and 1. And then we're going to add we're going to add all those trees to the accumulator. So how many possibilities are there? Well, we need only look at tree count left, the product of tree count left, and tree count right. So I've written tree create here instead. I'm sure many of you were looking at that with confusion or perhaps possibly scorn for my programming practice for the past few minutes. Now, why don't I exhibit what Professor Cormack was saying in lecture 14 about using build list to test your functions. So I'm going to build list from 0 to 10 with tree count. And if I haven't made any errors, which it appears I haven't, I will have a list outputted with the values of tree count from n equals 0 to 10. So there you have it. Try not to memorize this implementation, but to understand it and understand the approach, and then come back to it in half an hour and see if you can write your own, especially if you used a formula for both assignment 3 and 4 and have yet to write your own recursive implementation of this function. I strongly encourage you to try it. It's a lot of fun and it'll be very rewarding. Have a great reading week. Here are the practice problems. There's really only one more that I haven't already talked about. The first one is to implement general decorated trees. So this is a data structure with a mutually recursive definition. And the second one is to write your own tree count n after exercising the 30-minute rule. The last one is to write tree height min. Here's a little typo. It should say tree count min. I'll change that in the slides that I post. That works for arbitrarily large values. And you can do this by using the same strategy as above, by keeping the height as a parameter and subtracting 1 from the height every time, every recursive case, because you know you'll increase the height every time you recurse down by 1, and you have to throw out certain trees. In creative ways, I said, what about a tree of factors, or a tree of probability, or a family tree? Here's just a decorated tree. And if you wanted a tree of factors, you could write one similar to this, but 15, 5, and 3 here instead. So just think about that. See what kind of trees you can come up with. Thanks for watching. I hope that you can understand tree count if you didn't before. And I will see you after reading break.